All right. All right. Okay, so I'm Carl. I'm going to talk about the work that we've done here at Datadog, consolidating our query stack and using DataFusion to do that. So before time, we had a bunch of purpose-built query engines and kind of looked like this, where every single engine had a separate parser, had separate data stores. And so this meant that it was a complex mental model for the users to actually understand what was actually capable. And then there was limited compatibility. So you would go to one engine, some things would work that way. You would move to a different one and it would be a completely different set of semantics and data that was actually available there. And the architectures, basically they're built for the scale that we've had, but not necessarily the scale that we're looking at in the future. And the execution has been, even within like our SQL path, there were multiple different execution engines that worked similarly, but not quite the same. And then adding new capabilities was basically work on every single engine had to be redone. And so in particular, our SQL engine was a bit of a mess. So we had limited SQL support and every single new thing that any product team wanted to do required changes across 4 services. We had really leaky abstractions, so it used internals from our underlying engines directly, and basically they weren't able to evolve because of the tight coupling. And then even when we knew that some queries were being executed correctly, it was basically, you would change it just a little bit and it would look like a different query, but it wouldn't execute correctly. Or it would execute, but you wouldn't get the right data. And then it had a bunch of legacy formats that it needed to support. And initially it was a distributed only engine, and like eventually we made it run single node, but it always incurred this coordination overhead. And then it was very rigidly put together. So every single component knew basically way too much about everything else in the system. And so what we've been embarking over the past year and a half is really trying to break that apart. So the query languages that we support, we're translating those into Substrate, which is a relational algebra representation. Wendell will talk more about it. And it really establishes a common semantic space for all queries. And then the execution engines, basically we've broken apart the different components so that there isn't this direct correlation with the query languages. And we've been using DataFusion to really do that. So I'll quickly go over Substrate just because it is basically one of the things that really enabled everything for us to be able to break this apart. And what it really does is it breaks the language from the execution engine for us. So it doesn't matter whether it's SQL or whether it's our like Elasticsearch query or metrics. We can represent that within Substrate, and then we can figure out which engine to actually execute this on. So because the two are broken apart, we can actually transition from our old SQL engine to DataFusion. And it's extremely extensible. So if even where things don't fit into relational algebra, we've been able to extend it. And so we've used DataFusion as the like preferred engine for this data platform. So Substrate is generated by whichever product is parsing. Then we can execute almost all of that on DataFusion. And then we have custom connectors to actually get the data out of the underlying storage. And so we found this to be a really flexible and efficient way of doing things. So we have S3 access. We have connectors to all of the underlying databases that we have. We can really tune the caching that we need at different layers. And then we're building distributed execution into our DataFusion so that we can actually normally process things single node, but where we need it, we can scale up. And then all of this provides a single execution engine, so everything kind of works together. So it doesn't matter whether you're querying with the events or metrics, the queries all look the same. And so this is difficult to read, but basically we've been able to move all of the traffic that used to run on all of these different execution engines over to DataFusion. Even the little bumps at the end, that's actually still DataFusion. It's just that we have a new intermediate that we're starting to roll out. But the Malamute, which is our old execution engine, is down to 0 QPS, which was a huge accomplishment, and it moved fast. It's been basically a year and a half that we've been working on this. And so overall, we built this federated platform. Substrate gives us the language. Arrow is compatible with all of our use cases. And then we've been using DataFusion to power the execution. And for Datadog, it's been really important to contribute back to open source. So we've been able to use DataFusion at scale. Like we're running 68 million DataFusion queries per hour. And like we found some performance optimizations that we want to make, and we're going to contribute them. We've had a lot of bug fixes in the substrate integration, and we've really been embracing a community first, trying to upstream the changes instead of doing it in a private fork. And with that, I'll turn it over to Wendell.
Hi, everyone. I'm Wendell. I also work here at Datadog with Carl and with Mia. So thanks for coming. Glad to see you here. Yeah, as you just heard from Carl, we're doing a lot of stuff with DataFusion. We're adopting it as our preferred engine, but we're trying to integrate it with a lot of other components. And when you try and integrate it into a system with a lot of other components, you need to figure out how to do that. How does it fit together with all the other pieces? And the main way we've done that is via Substrate. It's been kind of the glue that allows us to connect DataFusion with these other components and these other components with each other. And I'm going to go through a little bit of how that works. So just to reiterate, Carl talked a little bit about some of the challenges we've had here. At least one of them is that we've got several different languages. We've got one for metrics queries and dashboard graphs, which works in a very particular way. We've got logs and trace queries. That's a more elastic search-based language, much more similar to that. And then more recently, we've added SQL as a thing users can use. And all three of these have independent histories. None of them is built on the other. So they've all got different semantics, different data models, and we're all trying to use them on top of different data sources. So how do you fit that together? So now I'm coming back to a slide that I half stole from Andrew, just to bring it back up here. In case you aren't sick yet of hearing any LLVM comparisons, I have yet another one for you. So yeah, there's LLVM, which is intermediate representations are a classic way to get intercompatibility. It's what LLVM uses. Another comparison would be the JVM. You could use that here too, but the basic idea is you have got different front ends. Then you compile to an intermediate representation, and then that allows you to use one compiler engine, whatever you want to call it, to be able to handle all these different front ends and to combine all the optimizations and performance and semantics in that one place so that you can develop the front ends separately. And for us, that's exactly what we're doing with Substrate and with DataFusion. We've got our 3 different languages. We compile to an intermediate representation, which is Substrate. And then from there, we can go on to a planner and an engine. And the why is the composable data systems, like we've been talking about. There's a paper called the Composable Data Management System out there. There's a bunch of other papers around that you can find that say similar sorts of things. That's what we're trying to do. And basically the idea is that you have a front end, you've got an intermediate representation, you can have an optimizer, then you can have another intermediate representation. With Substrate, it can be either the logical layer, which is before the optimizations, which just talks about the semantics of what you're trying to do without worrying about how it actually maps to the actual physical data. Then after the query optimizer, you've got the physical layer. So, or what DataFusion calls an execution plan, and that maps to, and that's very specifically like the algorithms you would use and how you actually access the data. And Substrate has capabilities there as well. But by using a composable data system like this, by separating out these pieces, it allows you to fit together different parsers with different optimizers, with different libraries, with different runtimes if you wanted. That's at least the general idea. That's a lot of what we're having to try and do here because we already have multiple languages. We have multiple engines. DataFusion is becoming our preferred one, but we still have to support the others until we can get everything entirely off of them. And we're working out the optimization, which works differently on some of our different stacks. So what is Substrate? What is the basis for it? So many of you here will be familiar with relational algebra. Many of you maybe less so. You may not know exactly how some of this works, but relational algebra is something that is actually really fundamental to databases. It actually precedes SQL. SQL was built to represent as a textual way to represent relational algebra in like ways that humans could put into text. And it's a very mathematical CS framework for how you do queries. And Substrate itself is meant to encode relational algebra. It's a way to take it and encode it in a way that is cross-language compatible. So it's built on top of protobuf. So it's really just a bunch of basically protobuf messages that you can just import and use from any language that then you can then send to or receive from, say, Calcite for optimization, or send to or receive from DataFusion. And relational algebra itself is kind of the basis for DataFusion logical plans and for physical plans or execution plans, and also for planners pretty much everywhere. They're all pretty much relational algebra based, at least what I know of them. In terms of by example, so here I have a Datadog metrics query. This was not written for relational algebra systems. This was built for a metrics system, a time series database that really was not meant to be relational. It was very specific in what it could do. But the point of relational algebra is to be very generic, right? It's to be able to represent all sorts of queries and to decompose them into the operations that you actually need to do. So this is at the logical layer, and if you take like that's our metrics query language, and if you map it to the various different operations, basically you start at the bottom, you do a read from the system.cpu.usage metric. The next operation is a filter. You filter by, in this case, whether the tag env is equal to prod, which is, in relational systems, that could be a column. We call it a tag, but really, what's the difference? Next layer up is you do an aggregation. Here it's an aggregation in time. So this is a grouping by time as well as by another tag, and you do a maximum. And then there's another layer of aggregation on top of that. So this is basically like an example of how relational algebra works. Here it's just 4 operations in a row, so it's a linear plan. But actually relational algebra can be a tree or even a directed acyclic graph of operations. So Substrate is a representation of that, and you can use it today. It's built on protobuf, so you can generate plans from any language. There's a number of different libraries in different languages like Go and Python and Rust that you can use to build these. There's a DataFusion substrate crate you already saw from the history since the beginning of time of DataFusion earlier that it was added a few years ago. So you can parse and execute substrate plans directly. It works with Calcite. It's also something you can use with ADBC, which is in Arrow database connector, and also with Aeroflight. They all accept substrate or SQL. Note here I say which dialect because that's one of the challenges with SQL. There's so many different dialects. What do any of them mean? Substrate tries to be sort of a way of specifying explicitly what you mean in one way, even across dialects. Whereas, if you were trying and use SQL with all three of these, you might end up with some challenges there dealing with the dialect problem. Or you can bring your own language. That's kind of what we need to do. You can bring your own language. You can build your own parser. That's its own challenge to begin with, but you're going to have to do that anyway. But if you can compile it to substrate, then DataFusion or whatever you want can be your execution engine. But DataFusion is a pretty good one. That's why we're all here. Anyways, that's all I have. So thank you. And thank you for coming. And I'll hand it off to Dewey, I think is next.
That didn't end up on that show.
Oh, no.
Yeah, sorry.
Okay.
All I need is a web. I need a web browser. Is that okay?
Yeah.
Okay.
There you go.
Must load for a second. Well, yeah, there we go. Oh, so good. Not very good. Thanks. Yeah, I'm here to tell you today about SedonaDB, which we built on DataFusion. It was not included in Andrew's list because it's rather new. So yeah, just a tiny bit about me. I came from the Arrow world. I built NanoArrow, which is a implementation of Arrow in C, and I built. When I was there, I was working with Joris Vandenbosch, who's a GeoPandas maintainer, and Kyle Barron, who worked on GeoDataFusion, which some of you may have heard about in the New York City meetup. And we made GeoArrow together. So that's like a convention for dealing with these geometry and geography types in Arrow. And I worked on some R worlds stuff. And most recently, I worked on Apache Sedona, which is a project the creators of that started a company called Wherobots. And our main offering is based on Spark. But I think the work that you'll see tonight is a precursor to where we're headed. So yeah, this is from our documentation, and it's sufficiently dense that I'm actually not going to read it, and instead tell you that SedonaDB is a bunch of DataFusion components and interfaces. So a lot of the work that I do quite a lot of work on SedonaDB, and I build some of the components, and I do all the interfaces. But mostly this is the story of one query. We can obviously execute lots of stuff, but I'm just going to tell you about one. This is a spatial join. This is like the crux of the hard problem of what spatial query engines are mostly trying to do, where you have two different kinds of spatial things. In this case, we've got a bunch of polygons that define neighborhoods. This is Philadelphia. I tried to do Boston, but I couldn't find the data fast enough. And so you've got neighborhoods in Philadelphia. They've all got a little bit of a name. And then we have a bunch of parking tickets, which was derived from Philadelphia Open Data. And about 9 million parking tickets. And I don't know, like 20 or so polygons, pretty complex polygons. Neighborhoods have like pretty squiggly boundaries. And this is actually a very hard query to execute quickly if you don't have support for the spatial formats, and you don't have support for the operation itself, the spatial join. It turns out that counting all of those parking violations per polygon is pretty expensive to do if you don't do some smart things about it. And if you just back up a tiny bit, that query required a couple of things. Like we had to have a way to execute it. Like you can't just type SQL into your terminal. So this is a Python package that you can install and load. And we had to be able to read a CSV file. DataFusion has a great CSV parser, so that wasn't a problem. But you have to be able to understand the geometry, make that into a type that these functions can understand. So we had to have some functions to make that happen. And we also had to be able to read this thing called GeoParquet, which Jake is about to tell you all about. But the city of Philadelphia distributes these things called neighborhoods.parquet, which is great. But it is a parquet file that DataFusion does not understand as geometry. So yeah, this is the DataFusion crowd. So I'm gonna talk to you about DataFusion internals. I hope you're ready. I hope that your credentials were checked at the door, that you're ready for this. And these are basically the four things that I'm gonna talk about. We have some scalar UDFs, we've got some file formats, we've got our own exec plan, which is fun. And we need an interface to make sure that someone can actually use this. So yeah, this is a scalar UDF. This is one of my favorite ones, the buffer. You take a point and you make it bigger. And yeah, and you have to be able to call these things and put them. And if you've written much DataFusion code, perhaps you've come across these, the scalar UDF, how you define a function. And yeah, there are a lot of them. So SedonityB, the version of it that I checked when I wrote this slide had 88 scalar functions and 5 aggregates. I added two have merged since then. Contributors merged 2 of them, which is fun. And I think we're about halfway to the ones that we support in Sedona Spark, or the ones that are in PostGIS, similar set. And also we had to implement like hundreds of these quite literally. So we weren't, and we had our own types that aren't supported in base DataFusion. So we had to do some things to make it so we didn't have to copy and paste code 88 times. So we've got this thing called the Sedona type, and Andrew's talking about user-defined types, and we would love to change that to be a DataFusion type of some kind. We run things, we can't use the signature because signature is built on a data type abstraction that can't support geometry, so we had to invent that. But for the most part, these things are pretty straightforward to write. Yeah, file formats. I'm going to skip talking too much about GeoParquet because Jacob will give you a way more comprehensive example, but this is the main high performance file format for spatial. Like if you want to dump a bunch of things into a bunch of geometry, then Parquet is a great way to do it. And before Parquet actually had a way to do this, a bunch of people got together and made GeoParquet. And it was actually turns out incredibly widely adopted. I didn't actually, I thought I was going to be pulling shape files from the city of Philadelphia, and it turns out they distributed GeoParquet. But yeah, lots of people support this. So we had to have a way to read it. This is the thing that people are doing to have enough data for this to be useful for them. And yeah, it's just a rough, in the first 25 lines of that file. And the other 5,000 lines of that file it's not 5,000, it's quite a bit though. It actually turns out this is not as easy as I thought it was going to be. But we did it, and you can now select all from a Parquet file, just like you would with a normal Parquet file, and it gets your geometry columns right. And does all your pruning, which is another big one. So yeah, also we have so many file formats. Spatial has been around for a long time, and a lot of these file formats are widely used. So we had to make a bit of a helper for that one too, because there's just so many of them. And yeah, this is not quite merged, but that should be out not too long. And yeah, I mentioned the spatial join. So again, this problem where we have many spatial things over here and many spatial things over here, and you need to check whether every single point is in every single polygon. If you have to do that, you've lost, and you will be waiting a long time. But if you were to sort of leave DataFusion to its own devices, it will very happily chug away and do that for you, which I appreciate it for, but we needed something better. So yeah, we have this thing called the spatial join exec, and we have an optimizer rule to stick it in there. I can't take any credit for it. My colleague Kristen, or Continuation, if you spot him on the comment or DataFusion repos, he implemented this, and the in-core, the in-memory version of this, which is quite similar to a hash join, Yeah, he's working on the out-of-core version of it, which is quite similar to a hybrid hash. Yeah, should be out in a few weeks. Yeah, and we needed this interface. Like, we need to print stuff. When someone types a query, you need to be able to show what happened. And if you try to do this today, if we use stock DataFusion to do this, then you end up seeing a lot of binary. Yeah, we wanted people to see a text representation of that. So I had to build a table printer. I'm quite proud of this table printer. And I hope it goes in DataFusion at some point. And I had to make a schema printer too. Like, some of these, if this printed out by default, I think you'd actually just see binary today. I don't think it would show you any metadata, or if it did, it would give you a dump of the debug fields representation, which is pretty verbose. So yeah, we had to do a bit of this. We also needed some way to get some of these Python objects people are interacting with. Yeah, if you have two pandas, if you have some spatial stuff, and people are expecting a geodata frame out of that from GeoPandas. And that's not too hard for us to do, since we control the interface. And yeah, so that works. It also works headed in the other direction. Like, if you have some spatial thing, or actually any arrow-based thing, it will very happily stream it back into Sedona. You can do fun things like stream stuff from DuckDB to SedonaDB, back to DuckDB if you really want to. Or do your spatial join and SedonaDB, and do your integrate with the other stuff in DuckDB. We don't really care about that, but we will very happily stream stuff in and out for you, as long as it can speak arrow. And yeah, so I mean, if any of you are working in this world, you will spot that this is not actually a new thing. So that all the things that I just showed you, you have been able to do that for the last 20 years in PostGIS. And DuckDB also has a spatial extension, which provides some of this. Sedona Spark provides all of this and more. And so why did we bother? There's a number of reasons, but this is the first one, is that it's very fast. It's incredibly fast to do this. There's no TCPH for spatial, so we had to make one in order to show ourselves to be faster. And also to fix all of the performance issues that happened before we made this diagram. And there were a number of them. You'll see Q5 is actually, we're actually not faster, which is I screwed up. That's my fault. I didn't implement the groups accumulator. Anyway, but
you wouldn't believe it if you were faster. That was one query you're slowing.
Well, yeah, that's one of the reasons I didn't fix it before we published this. And also I didn't have time, but still. Yeah, and it is very fast. And sort of the left hand, these are the same queries. It's hard to make these queries. They're not perfect, but the left half is a scale factor 1. The right half is a scale factor 10. These things are arbitrary. We made them up, but basically, as the data gets bigger, we're trying to figure out at what point does other stuff start failing and not being able to execute. And it turns out there's a lot of stuff. It doesn't take too much data for the existing infrastructure to fall apart. And because we had control over all the pieces, and DataFusion let us extend all the pieces, we could make an engine that could do that. Yeah, I have to acknowledge the DataFusion community for making all this possible for us. Particularly Tim Saucer, his work on the metadata really helped us integrate with the rest of DataFusion in a way that we would have had a giant workaround to do otherwise. Andrew reviewed a lot of PRs for us, and thank you. And then my colleagues at Wherobots also, you know, I did the wiring, but they did a lot of the parts, and they're fantastic. Yeah, thank you.
So this link did not work. Oh, there it goes.
You click on this one, so they want to use it. This one, if you want to use this one, you
I'll just do it here.
intersection.
Let's see.
Recording in progress.
Sorry. Okay. Where's my slide here? Okay. slideshow. Okay, thanks. I accidentally put my slides on the corporate Google Slides account, and if I export them, it would be a lot of paperwork and stuff. So that was my mistake. So anyway, okay. My name is Jake Wasserman. I work at Meta. I'm going to talk a little bit about GeoParquet. The spatial community is pretty small, but we like to be like really loud and obnoxious. So you get 2 spatial talks tonight. I'm not actually like a database engineer or even a data infra engineer per se, but I do a lot of work with spatial data. I did a lot of work with Parquet and got a chance to work with Dewey on this GeoParquet format. So I messaged Andrew when I saw this was coming up. He was like, yeah, it sounds interesting. So anyway, yeah, I work on the maps team at Meta. One of the cool things I get to do is work on this project called the Overture Maps Foundation. So it's a foundation that was founded by AWS, Meta, Microsoft, and TomTom. That's run by the Linux Foundation. And kind of our main goal here is we publish global open map data standardized to a common schema. It has quality and validation, standard QA guarantees. It's basically the same data that we use at Meta anywhere a map is seen on a Facebook surface or a Meta surface. So Facebook, Instagram, WhatsApp. If you've seen anything on the new like Meta display classes that have maps, like this is actually all coming from Overture. So we participate in this foundation with our colleagues at these other companies. We produce these global map data sets. We use these at Meta. And it's all free and open. You can download it from S3. I'll talk a little bit more about it here. So just for some quick background. So Overture publishes these 6 data themes. There's an addresses, points layer, base, which is sort of like everything when you see on a map, that's like the water and the land and the infrastructure and parks and all that kind of stuff, sort of wrapped up in this base layer. Building footprints, administrative borders and boundaries, places, which are like business listings, and an entire transportation network that's like the road network, how to navigate, pedestrian, railroads, all that kind of stuff. If you look over here, I just ran the query of what kind of counts we have on those things. So like 500 million address points. Sort of the hallmark of the data set is like 2.5 billion buildings. So it's conflated from a number of data sources. I think we've got pretty solid global building coverage. So if you're ever interested in like building data, we've got you covered there. I realized too, I've given a talk like this before where I'm talking about Parquet to like a spatial data community. And I know we were talking, and Wendell yesterday was like, what is actually a geometry? Like, what do you actually mean by this? So I wanted to include sort of a bit of a primer on geometries and what we actually mean when we're talking about that. So if you go to this website, explore.overturemaps.org, it has like sort of an X-ray view of the map data. You can click on all the components. And geometry data types, this is what we talk about, is there's points, line strings, polygons, then there's these multi-types. So a point would be like if I'm labeling exactly where to put a label on a map, or an entrance pin, something that's sort of infinitesimally small. Line strings are like road segments, you can see them there. Polygons would be like a building footprint or a park polygon, things like that. I just highlighted here the building we're standing in, and I pulled up its sort of, this is this well-known text format, what that would look like here. So, you know, polygon is just an array of the coordinates that define the outline of the building. So anyway, so when we started the project, we got together and we were like, okay, we're publishing this plant scale spatial data. What format should we actually publish this in for ourselves? So, you know, Dewey was just talking about this. There's all these options like shapefiles, GeoJSON, flat GeoBuff, there's a whole bunch of things. Most of these are targeted towards like desktop software and browsers. There's not a lot that was really applicable to like a large plant scale data set. And since we were, you know, people from some big tech companies, we realized like all these pipelines are probably going to be written in Spark and Trino and Presto, and we're just going to ingest them back ourselves and ingest them into our own data warehouses. So like if these things are talking Parquet, we don't want to just like write these out to these other formats, like whatever, just keep them as Parquet and publish it. So we decided we're just going to release the Parquet files. This was kind of like controversial for an open data project because most open like geospatial formats expect this other thing. So we sort of got a lot of flack from that from the community. People were actually like really mad and curse at us and stuff like that, all because, you know, we were giving them free data in a format they didn't like. So anyway, so we started publishing these as Parquet, and then we found out there's a bunch of people working on kind of a similar problem, which Dewey was working on. And they had published this GeoParquet spec. So they were trying to say, okay, how can we standardize including spatial data into Parquet? It's essentially the question. And so it's really a very simple thing. The one thing is we have geometry data is encoded in what's called well-known binary, which is a very common geometry encoding for all the different geometry types that I just was talking about before. Put that in a byte array Parquet column. And then there's one other thing I think people forget about is Parquet has this little key value metadata in the footer that you can put anything you want in. Usually it's kind of like the writer will put their version or something like that. But they were already kind of standardizing on putting this geo key, which has this JSON blob that as long as you standardize on that, if you have this key, it tells you where the geometry column is, what it's called, like you are now geo Parquet. Then it was like, all right, just go into a whole bunch of spatial libraries, standardize on that. If they're all looking for that, like we can all agree, this is how we're gonna, distribute spatial data. So that was there. And that started to make good progress. Like it was implemented in GeoPandas, this thing called the Geospatial Data Abstraction Library, which is used basically everywhere. But the problem is the way it was working was it was super slow if you wanted to download a small region. So if you took that buildings data set, there's 2.5 billion buildings, and you're like, I'm interested in what's in Boston. There's no easy way to do it. You basically had to download the whole data set. So, we started to ask, how can we leverage sort of these predicate filter pushdowns on spatial data as we had it defined in GeoParquet? So the way we do this typically in spatial data, there's a spatial index here where you have your geometries at these leaf nodes, and what you do is you take the bounding boxes to what the spatial extents are of every geometry, and if you can group them together, you get sort of larger and larger bounding boxes up until the top. And if you're doing something like which of these buildings contain this point, what you do is you start at the top, and of course you start filtering out for the bounding boxes that will contain the point. And then once you get to those leaves, you then do a much more complicated operation where they can take a full sort of high resolution polygon and try to figure out, is the point inside the polygon or outside? So we're trying to people were debating, how do we do this? And the answer is actually kind of simple, which is to include the bounding box coordinates as explicit columns in the Parquet file. So before we just had, these geometry binary blobs. As long as we have a bbox column that has the xmin, ymin, xmax, and ymax, we can pull off something like the archery. And the real sort of realization here, like on the bottom right, is if you think about a row group that has these 4 bounding boxes in them, and if we store those, the corners of the bounding box as columns, sort of the row group summary statistics, that's computing the min and max of all the bounding boxes. Essentially, the row group summary is the bounding box of all of the geometries inside the row group, which is sort of this fundamental building block of building up spatial indexes. So, and then we said, okay, well, you can do that, but the key thing is you've got to actually cluster and order your data right. This was a lot of work that I had done. Before, we weren't really doing much of anything. And if you look on the left, those are the bounding boxes of the row groups of the data that we were originally distributing. Then we worked on doing sort of smarter sort, which you can see on the right, which is now, things are much better clustered. So if we do, you can now do this kind of query here. We're explicitly calling out your bounding boxes and using those columns for, this is something around the city of Boston. And you can process, obviously, 90 megabytes of what is a 240 gigabyte data set sitting on S3. So anyway, so we did that. That became GeoParquet 1.1. And then what we realized is, what you've got is a lot of bounding box data that's now sitting in your files. So if you look over here, right, you've got your geometry and your X and Ys. So I think Dewey did some math to find there's like 25 gigs of just bounding box data sitting there in the buildings data set. And this is like especially egregious for points because like over here, your geometry is a point. So it's like basically a binary representation of, there's something that says a point, X and Y. And then you've got X min and Y min, which are the point coordinates again. And then you've got the X max and Y max, which is the same thing. So it sort of triples up. It's like really bad. And so wouldn't it be nice if we just care about row group filtering to just not need that column and be able to put the bounding box coordinates into the row group summary statistics without the entire column, which is essentially what the new geometry data type is in Parquet. So it removes the need for that bounding box column, saves a lot of space, preserves push down filter ability for spatial queries. I know I wasn't actually involved in this part. I know Dewey did a lot of work, but this was recently merged into this Parquet version. So anyway, yeah, that's really all I got. So there's these new geometry types in Parquet. There's one for geography too to indicate something's on ellipsoid or spherical or spheroid. Reasonably fast to query remotely. If anyone is interested in spatial data for any reason, whether that's making maps, doing data analysis, this stuff is all free for you to download. We don't even have requester pays. You can just download it. That's it.
Cool. Thank you. Can I just share screen? That's correct, I'm sharing. Can I just use your computer? Yeah, you got this up already? I did this whole cool preparation where I got ready to live code on my computer and dropped the DataFusion CLI. And then I realized I forgot to ask for a microphone stand. And I'm not going to type this time.
Well, someone can hold your microphone while you code.
Yeah, that'll work. Okay, cool. I'm here today to talk to you about what I do best, pushing the limits. Past window functions, I guess. So got a couple of obligatory marketing slides here. I'm Brent, in case you haven't met me yet. And I'm just kind of a software engineering generalist. I've bounced around from telephony, voice over IP, low-level USB, Android embedded, a little bit of geospatial stuff, CAD. And I'm in databases. I don't know how that happened. And I've been with Coralogix for about 3 years, and we're a great company, so come talk to us. And Dan right here. And yeah, young startup, 2017, lots of data, yeah, 415 million raised, and billion in revenue or something, I don't know. More marketing sites. So let's get to the fun stuff. I used to be a teacher, and believe it or not, from the quality of this presentation, I used to do this for a living for a couple of years. So I gotta have objectives. So the first is I'd like you all to be able to describe why limit pushdown is important in database engines, and explain why pushing past window functions was tricky. And then name some instances when it can be done and when it can't be. So yeah, first of all, like, why would we go push limits? And so hopefully you can all see it up here. Do I need to make this bigger? We can talk through it. So the first one is just creating a table called nums, and it's just got a single column in it called sequence, and it's got 20 numbers, 0 through 20, 19. And then when we do an explain analyze on this, we're gonna like insert expensive function here. And so what I've got is just like a SHA-512, pretend it's decrypt or something actually expensive. So why do we want to push limits down? Well, I commented out the optimizer rule that did push limits. And what we got here is on a table of 20 numbers, we see that that SHA-512 is being calculated 20 times. And then we throw 17 of those away, and we come up with this limit 3, because we're asking for just the top 3 there. So obviously not something that you want to be doing if you don't have to. And believe me, it just gets worse with distributed queries and sorts and partitions and all that. So optimized, we clearly just want to go take that output rows 3, push that limit down onto our data source, ideally. So we don't even need to read more than 3 rows from the table. And then lo and behold, we're only calculating that expensive value 3 times. So better than 20. So why does this get difficult with window functions? Well, first of all, what is a window function? Believe it or not, I did a lot of SQL in my career, and somehow it was all relational and business reports, and I never worked with time series, and so I honestly didn't know much about window functions going into this. So I'm just going to start from the beginning. Window function is the only thing that I know of in SQL, aside from, I guess, a join, that allows row to access information about other rows around it. So in this silly example here, we're just going to calculate the moving average of sales data. So let's just say for some reason you wanted to do this. Maybe your sales data is really cyclical. So what we could do is create a table here, insert a bunch of these records into it, which is just simply a unique date and the total amount of sales on that date. And we can see that this is adding a moving average column to it. So let's talk about how that's calculated. So first off, so for each row, we're going to be calculating a row in this output table here. And the first example is kind of more interesting because we said like we wanted 1 preceding row and 1 following row, right? And so on our first row, there just is no preceding row, right? So we're not taking the average of before and after, we're just taking the average of these first 2 rows, the current row and the one after. So which gets us to like our first interesting question here, which is like, wait, what the heck is happening? We had our first like acausal read. And so we're pulling in a row that we haven't seen yet from the future. So that complicates things a little bit. So then the next example will be simplified again. So all right, our second row, we're just averaging these 3 values. And for our final row, just the next 3 values. But so what just happened there? Well, we only want, our limit was 3 rows that we want to push down, but we had to read 4 values to go calculate that. So that makes it more interesting. So how can we work around this problem? So with our unoptimized plan, what the DataFusion was doing prior to this optimizer rule was just saying, hey, I've got a fetch of 3, I've got a bounded window aggregate exec that needs some rows from the future, and so I can't push that limit down. So I'm just going to go scan 1 billion rows in my table and then hold them all in memory and then sort them all and then throw 99% of those rows out. So if you look at this, I mean, that's basically due to the acausal nature of this, because we needed to read that row from the future. So all we really have to do is go take a look at that fetch, see that it's followed by a window by and sort, and say, hey, we need to take this 3, add the 1 following row. Now we know we need 4 rows. Boom, we can push that down, which lets you do cool stuff like not just go push this down to the top K sort, but continue to push it down possibly all the way into your table provider. So if you have cool stuff like range indexing, or if you do sort preserving margin merge execs, where this is like partition and parallel, then it saves you a lot more work. So I guess the only thing to know about this is just that it's specific to rows. And so thinking about this, like maybe it's possible to generalize to ranges and. But you need like new operators and stuff. And it's questionable, and that's probably just the window function itself. So there's specific cases like rows where we know exactly how much we need to extend this limit that make it possible. So yeah, that's basically it. Like the only questions that we actually came to when implementing this was like, where do you put it? And if we look back at this plan, like this sort exec isn't inserted until the physical planner or optimizer actually goes and looks at this window aggregate exec and sees that it needs data sorted, and then it goes and inserts the sort. So got to put it after that. And then there's this existing rule called limit pushdown where it pushes down those limits. And so we want to take advantage of that, because once we get it down here, we want it to continue to go on its journey as far down as it can go. So we just inserted that right in between those two. And yeah, I will spare you the walking through the code review of this. Suffice to say, it's really simple. It's just basically a state machine that's walking the tree, finding limits, growing them if necessary, and then applying them when it hits the correct nodes. So if you haven't implemented an optimizer rule for DataFusion before, then hopefully this talk made you unintimidated about it. And if you've ever wondered about window functions, well, now you know. And shameless plug, Coralogix is always hiring, although unfortunately not for my team, I was informed today. So you missed that boat, probably be doing again next year, so come talk to us. Thanks a lot.
Is Josh live? Yes, Josh. You want to go? Oh no, yeah.
Oh, sure.
And 10-15 minutes.
Yeah, so I'm Jonathan. I'm a student at Western University. It's a university in Canada, just like 3 hours west of Toronto. I think you guys know Toronto. And today I'll be presenting niche join algorithms and kind of like when they're used. So yeah, just to do like a really quick review. These are kind of like the standard join algorithms that DataFusion currently supports. I'm not sure how technical everyone is here, so I'm just gonna go like do really quick sort of rundown of how each one works. So there's the hash join, which is I put a quality join under because it's usually used for cases where, or it's specifically used for cases where you're just trying to find like a equal predicate between two tables. And essentially how that works is you build up a hash table with one of the tables or on the Q column, you kind of hash it all, and then you kind of hash another table, and you kind of index into the hash table with the hashes that you created before, and you kind of try to match them. Whatever matches is your kind of how your join gets results. The next one is a storage join. This one's especially special in DataFusion because currently it's the only join that really supports good spelling. Hash spelling is going to be worked on. It's quite important for engines in general. The way storage join works is you essentially have kind of two tickers on both, or two pointers on both tables, and you kind of compare each one. Whenever you find a match, you advance the pointer to the next value, and you just kind of edit those matches. The final one, which is going to be a little important today because it deals with inequality predicates, is an S loop join. Essentially, if you were to try to find kind of matches between each table, I guess intuition, or you intuitively think you just write two double loops And you kind of just go through every single combination and see which kind of matches the condition or the predicate. And yeah, that's basically what it does. To the next slide. So yeah, so today I'll be focusing more on niche algorithms, which kind of some of them build off of the basic generic ones, but what you realize is what I would really focus on is that these are very simple concepts, but they're able to you kind of can see like the genius behind them. It really accelerates a lot of these different joins. So for perfect hash join, I kind of put when it's used, so it's kind of like a use case. So it's a little bit complete, but it's basically when one table has integer keys, inner join, and I kind of have unique keys, so there's no duplicate of any sort of key in that column. What this essentially allows you to do is you kind of can create an array, because there's no an array of the size of kind of like your min-max values on the build side. And what it allows you to do is you kind of hold the values from that array, and you can use arrows kernels to essentially index and do take. I don't know how many people are familiar with take. It's essentially when you kind of index into an array with I guess the values of your index or your key values. And so essentially does that, and it'll be able to quickly find all the matches for those two tables. And the next one, this one's kind of more important because I'll just be going over this simple Jordan concept today. It's called the piecewise version. It's just used when there's one range target. I'll explain how it works later. There's one that's particularly kind of cool. It's called the group hashing. And essentially what it does is, if you think about a group diagram, you kind of you're trying to take all columns in a certain column, or all values in a certain column, and take all ones that have a duplicate value, and kind of take a corresponding value in another column and kind of do sort of aggregation of it. So, for example, if you want to do like a sum, if you want to do like a min or max, that's essentially how it works. So if you think about it, because you're trying to find the same keys, what you can think of is that for an optimizer, when you realize, oh, both of my keys on the group by and hashing are pretty much the same, you're using the same key. What you can do is when you hash the hash table, you obviously when you go in the same bucket, that means the key duplicated, right? And what you do is use your aggregation, which is like your min, your max, or your sum, and you kind of just run that aggregation on the incoming values, and it kind of combines the two operations. As it joins, I think David was looking into it a little bit earlier. What this essentially does is it takes the first value in a predicate. So let's say you have a left value, and you kind of find the first value in the right table where it's less, or kind of fits the predicate where it's less than a certain value. But it's like the first value before a certain value. That's essentially what you're trying to find. It helps with sort of time series data. It's used a lot of that, especially with inequality joins, which is essentially when you have multiple range predicates, you can sort both tables, and you're able to use min-max index to basically find like the fastest matches very quickly using min-max index. So if that didn't make too much sense, I'm just going to be breaking down one of the joins, which is the piecewise inverse join. So the focus of piecewise inverse join is that it's just for single equality or single inequality predicates. And essentially what this is doing is you're able to sort the table, which you're able to sort the table when you, okay, let's just take a square, right? You are joining on table 1, table 2, I already sorted it in ascending order, and you're trying to find all the values, or you're trying to join it on the condition that all the values in the table 1 are larger than the values in table 2. And what this allows you to do is, okay, like when you first think of like SW join, which is what we executed this, where you kind of check every single possibility. Instead, what you can do is you compare each value So imagine this is a single partitioned execution in DataFusion, right? You have your buffered side, your stream side, and you kind of run a pointer on each side. And you kind of compare, right? You see, oh, 10 is 10 greater than 10? No, yeah, 10 is not greater than 10. So then you compare the next one. You're like, oh, it's 20 greater than 10. And what this allows you to do is that because you're only looking for all values that are greater than 10, you realize if it's in sorted order, all values after 20 are going to match the thing, or match the predicate. So what you're able to do with 10 is you're able to make all matches on the buffered side. And this kind of gives you you guys can see how it's very simple, but it gets you your matches really quick. And it uses a similar concept to sort merge join, where now, instead of having to recompare the next value, so which is 30, all the way from like starting from 10, you just start from 20 because you're guaranteed your left value to be not incorrect, or or it would be equal. So this is the performance. I shout out to Dunnington, which is one of the committers for DataFusion, who really helped me kind of push this to the finish line. He also reviewed a lot of PRs. If you guys want to read too, I guess, yeah, you guys can do that for DataFusion. So we see here there's a huge speedup for inner joins, lateral joins, right joins, full joins, and it's kind of showing speedup. You see like around 10x speedup, which is actually really good. I think it's quite easy to see how the algorithm itself is really helping instead of doing like an O of N's where that's the looping. There's also I don't know if some people here know what existence joins are. They're kind of like semi joins, anti joins, which is also called mark joins. It's kind of you're basically just trying to see which side of the table actually matches the predicate. You're just marking them down. So, for example, for that semi join, you're just seeing which values in this table 1 is able to satisfy the predicate even once when compared to table 2. So something interesting you can do here is that you can see how one table is sorted, right? So once the table is sorted ascending, while the other doesn't need to be sorted, it kind of saves the cost of having to not sort. You're just trying to, because you're trying to find a greater, so table 1, the ID is greater than table 2, the ID. What you can do is find the minimum value of table 2, which in this case is 10. And now you know you can go through table 1, hit the first match, and you know for sure those are the only ones that will match. If that kind of makes sense. This kind of follows the principle that, hey, if that's the lowest value, whatever is larger than that value will match at least once. So that leads to a huge speedup. And when we look at the performance for this, it kind of shows so all you really have to do is find the minimum or maximum value on the stream side and kind of iterate on your buffer side. And the first match you find that is completes your query, as long as your left side is sorted, which is what DataFusion can do with the enforcement required to put over Google. And yeah, you see huge speedups, like 480 times, 380 times. Like these are pretty substantial speedups. But yeah, I think that should be it for my talk. Thank you.
So we have some time. Anyone have any questions for our speakers today?
How do you get the minimum value on the streaming side without sorting?
You just iterate itself with that iteration, and then you just apply the minimum value.
So you have the streaming side in memory.
Yeah. What you can do is you can partition